Welcome, everybody. This is our weekly Open Programmable Infrastructure API weekly meeting. Today we have Red Hat presenting. Please share and let's get it going. Thank you.
Okay. You just let me know when you can see because everything has disappeared in true Zoom fashion.
It's up, we can see it.
Okay, cool. All right, great. So today we thought we might present a couple of slides just to generate some conversation around some of the thoughts that we've been having. And really it's just to help, us try to problem solve some of the issues that we think we might encounter. Or maybe they're, folks online think they're not really issues, in which case, let's discuss and see how it goes. Let me just close off this box here. So the first thing that we kind of tried to put together in terms of a view was a view of which data planes would be in operation once an IPU has offloaded, I guess, the tenant networking infrastructure. And one thing that occurred to us potentially is that in a lot of scenarios, people, and I guess, please correct me if I'm wrong in my assumption here, but in a lot of scenarios, we assumed that the Linux kernel on the DPU itself would be used as a software fallback or a slow path kind of data plane that would reflect the state of the accelerator-based data plane. Does that make sense to folks?
Yes.
Yep, it does.
Okay, which essentially brought us to the point of trying to consider where the OPI API would reside. So, it would be great if the OPI API, was used to define intent, and then whatever got translated from this layer on would basically control both kernel networking and the vendor-based data plane. And essentially, I guess between the actual vendor data plane and the Linux kernel, and I don't show it here, we would have something like a hardware abstraction based API, and that would really mirror state right across the two data planes that are in operation on the DPU. Is that what people thought this would look like, or are we shooting way off the mark here?
I mean, if I may, I believe that like your Linux kernel will be like the source of truth for the fast path. So
Okay.
you configure your Linux. Can you hear me?
Yes.
Yeah. So you configure all your networking objects in the Linux kernel, and then those networking objects gets written by some software, and they get translated to the fast path somehow.
Okay.
To the fast path configuration.
Yeah. And your expectation is that.
Sorry, carry on. When you go, Ted.
Your expectation is then that if the vendor data plane doesn't have the specific accelerator, it could still be implemented in software in the Linux kernel. So you get a consistent API experience, whether or not you have a particular hardware accelerator for a particular function.
Yeah, and I think more than what Mariam said so far, it seems like very often some of the control plane traffic might just run in the Linux kernel anyway and not be attempted to be accelerated in the hardware. Is that a fair statement as well? And when I
Yes,
say
I believe so. I mean,
Yeah.
for instance, if you have if you want to do ARP resolution, right?
Yes.
You don't need that to be in the fast path. You can just do that in the slow path, and then the when the resolution happens, then the subsequent packets can actually go through the fast path because you have already configured your fast path with the knowledge that you acquired by the ARP resolution operation.
Yes.
Vipin for the AMD Pensando with P4 pipeline acceleration, that's exactly the same case, or you see it completely different?
No, that's it over there. Hey, Boris, sorry. What was the question?
I'm asking if for AMD Pensando you see the same, or with P4 pipeline, everything implemented in P4, you see a different approach here.
Yeah, I'm trying to catch up. So the
So
Yeah,
so
maybe
the-
can you repeat, help Vipin?
Yeah, just to summarize for you, Vipin, what we're showing here is that whatever's in the accelerated data plane is like a subset of what is known by a kernel running on the DPU, and things like ARP messages and traffic like that would actually be handled by the kernel rather than by the hardware acceleration on the DPU.
yeah, I mean, as long as there's flexibility on what could be handled in the P4 or data path versus what could be handled in the kernel, that's good enough. We do process some control messages in data path or so-called P4, but not everything. So assuming that it'll always be like if you can, then you should, but if you don't have to, then if this particular proposal allows you to handle it in data path, that's great. Like otherwise, it's fine too.
Yeah, okay, so a different way of maybe describing it is you've got equivalent or a subset in the hardware path, and you'd never have a superset of configuration in the hardware path.
Yeah. I mean, it's not that you can handle all cases in the hardware path. So even if you do, it could be like fixed set of things that needs to be handled at a high speed. For example, let me take example of a BFD protocol. You probably want to handle it in the data path and not in the soft data path, which is kernel. If you have a high amount of, let's say you are catering to some specific DNS server, or you want to analyze DNS packets for certain things, then maybe you want to parse it in the data path and not in the control path. But having said that, it will be subjective to what use case you have, and more importantly, not everything will be handled in data path, and not all kinds of packets with all kinds of things will be handled in data path. But it'll be something that is specific to the use case is the way we see it here.
But it's always going to be the subset of the entire Linux kernel.
Yeah, it is going to be subset. Yeah, it won't be entire, subsuming the entire thing. No, it doesn't make sense to do everything that happens in kernel in the data path.
Yes, Venka.
The picture is a little.
So
medium.
if we look at, we're saying the Linux kernel is the main source of truth for networking, and then there is a P4 pipeline that accelerates some parts of it, right?
Just eat it and then make sure it's
and
looking better when you do it, so it's square.
Sorry,
Sorry, ignore me.
Can I go ahead?
Go ahead, Venka.
Yeah, so we are saying that Linux kernel is the single source of truth for networking in the DPU, and then there is a P4 pipeline which is an accelerator, and some of it will get offloaded, and that creates a fast path, and then suddenly the kernel becomes a slow path, right? And then, but there is a statement made, it's maybe a little too broad, that what is in the P4 pipeline is a subset of what is in the Linux kernel. Yes, when you have fast path and slow path, fast path seems to usually have like the 80-20 or 90-10 rule. You try to move, most packets, but less functionality into hardware. And there are always some complicated things like IP options and things like that, which hardware doesn't handle. We keep it in the kernel. So up to this, I'm okay with what he said, but we have to leave open for additional extensions to the P4 pipeline. The P4 pipelines can be, it could be a modular and composable and extendable data plane. We have to leave room for extendability that may not directly come through the Linux kernel, but there could be something else, almost like a multi-tenancy. I don't want to digress, but maybe we just should leave that room open, that the P4 pipeline itself might have multiple masters and they are handled properly from multiple kernels. The reason I'm saying it is because that is being adopted in multiple places. I remember in pins, there was some discussion and things like that. So we don't want it to be strict. Yeah, what comes from the kernel is a subset of what kernel handles is an okay assumption, but we should assume that there could be other things going on and accelerated on the DP, just as a generic model.
Yeah, okay, so understood. So there needs to be scope for P4 data plane only features.
Yeah, so one of the customers could add an extension which is kind of extension the whole OPI stack, right? And then as long as the P4 architecture there describes how that new addition interacts with this, basically it's a composable data plane, these two can interact and those models exist, and leaving that room is a good way to start, especially because this happens to be the lowest layer. The lowest layers of the stacks, we want to keep it a little more programmable and extendable. As you go higher, so again, I'm making broad statements. Correct me if I'm wrong or we don't agree. So that's the reason we want to leave that room open.
Thanks, Venkat. Dimitrios, you have your hands up. I know Toshi, you tried to speak up. So if you want to be queued, just raise your hand and we can hear your comments as well, Toshi. And Miriam, for the interest of time, just guide me if you want to pause the questions for a second and then go through the slides a little bit more before we jump back to the questions, because probably you have more than one slide.
I have more than one slide, but this is an important conversation, so I'm happy to let it run,
Okay, cool.
Yeah.
So Dimitrios and then Toshi. Go ahead.
Yeah, thank you. One question to what Venkat said. Are we talking about maybe the possibility of the applications to actually offload their own functionalities into the data plane directly? Are we talking about this kind of use cases?
Yeah, so it may not be offload, may not be how I would characterize, but imagine we have a full OPI stack. There is an application running, it comes through all the way down, programs the P4 pipeline. So everything is cool. But we can very easily imagine another control plane coming and adding something else into the P4 pipeline, right? To get some additional functionality. A simplest example I can give is some telemetry, right? Some other application comes and says, hey, I want to see what's going on between this part of the pipeline and an application. Or somebody could be saying, I want to count every 10th packet. These are harmless way of adding new functionality to the P4 pipeline. And it's possible that they may not come through the Linux kernel stack. They may come through from something else. So just leaving that up, that the P4 pipeline that's at the bottom of this whole stack is flexible and might have multiple masters is important to leave it. It does come with complications, like I said, multiple heads and multiple controllers, but they are being solved in a separate way.
Yeah, okay, I agree. Yeah.
Toshi?
Yes, I think it depends on the setup or implementation, but I'm thinking more toward the model, the SRV virtual functions is directly or can be directly attached to the pod or virtual machine on a host. In such model, the bridging is performed by the hardware layer, the pipeline. The traffic is not bridged in the kernel. And so this picture kind of hinting by the dotted red line, the traffic is bridged by the Linux kernel. But the model I'm basically thinking in my mind is the traffic is bridged by the hardware layer. And we can program the ACO or load balancing to the flow table maintained by the hardware. And you can use the TC Flower to basically a hardware offload and program to the flow table to the hardware. And if the flow table is missed, then the exception is raised to the ARM complex. And then it basically programs the flow table and recirculate, resubmit to the hardware, and then performed. So either way, the flow table is missed or hit, and miss its upcode to the ARM complex, but still bridged in the hardware layer. That's the kind of the model I'm basically having in my mind.
So I guess one way to kind of describe that back, just to ensure I understand what you're saying, is that there can be a kind of hybrid model where at least the bridging part of the slow path is still happening in the hardware data plane, but that you for exceptions you would have to redirect packets to the kernel.
Right. The hardware typically manage the flow table or maybe the connection tracking table, depending on if it is layer 2 or layer 3 or type of things. And if I think this model might look something like a Mellanox ASAP tool. Then if you hit the flow table, then you are not actually using the ARM core to dispatch the traffic. And if the flow table is missed, then just like OVS, basically it needs to upcall. And upcall is made to the Linux kernel, and or maybe the user space. And then that agent basically program the flow table, right? And the implementation doesn't actually require the Linux kernel either. I mean, there could be all the slow paths may be implemented in the user space, like a Sonic. Sonic is basically the switch operating system, but it has basically all kinds of agent or SDK layer implemented in a user space. And that the app call is basically forwarded to the agent on the user space. And that's the one basically perform the programming through the SDK layer in a user space. And of course, the programming goes through the kernel, but kernel is not really dispatching the traffic as this red dot line kind of indicates.
Yeah, okay, understood. So in that case, there's a user space equivalent of what the red lines in the kernel are doing in this diagram.
Right. I think this model is more like a accelerator model. You could have like a ConnectX on a host, and you enable the TC Flower with hardware offloading. Then I agree, it works just like this. But
Yeah, it might be no harm, Toshi, if you drew it out. Would you be willing to draw that out and bring it back, just so we can have a look, another detailed look through it? Because while I followed what you were saying, I guess it'd be good to document it as well, you know?
sure.
I know.
Great.
So Mayor McDonald, I mean, I know we had another drawing where instead of Linux kernel, we kind of showed where, it could be user space or Linux kernel. I mean, I think that the point though is that you've got a fast path and a slow path. So we could say in this picture, Linux kernel / like user space data plane, correct?
I agree with that. I think it shouldn't be Linux kernel mandatorily. I think what we are talking about, the split between soft path versus the fast path.
Right.
I mean, many
Yeah, I mean, we could make that
DPDK-based user
update.
space applications would use something like that.
Yeah, but DPDK, when we talk about DPDK user space applications, like, forgive me for my ignorance here, they're typically pure data plane packet processing applications, and they use other things for their control plane, like FRR or something implemented completely from scratch, right? What I'm trying to reflect is that DPDK doesn't give you the control plane smarts to program.
Yeah, DPDK wouldn't give control plane smarts. It is really the soft data path that VPP will process things on, and or VPP/DPDK/user plane function, and you won't rely strictly on the kernel to do it. So that's where I think I was agreeing with the comment that it doesn't have to be kernel. It can very well be the it can very well be this process, right?
Yeah, that's fair enough.
Thanks.
And not to complicate this picture further, but potentially, I guess it is a complication. One thing we were thinking about was, in the scenario where we have separated tenant cluster and an infrastructure cluster, because that's kind of where our focus is at the moment. If we use this, well, specifically in the case of the Linux kernel, if we use the Linux kernel as the fallback or the slow path, then potentially, we would need to use something like VRFs, because the infrastructure itself will have its own CNI and its own networking and all of that good stuff also running on the DPU. Is that something people have considered or thought about, or any thoughts?
If you want to use VPNs, then you need VRFs. If we're talking about layer 3 VPNs. And of course, you need routing tables that are different for global routing domain, which means the routing of the infrastructure packets, let's say, and different VRFs per VPN when you want to actually handle tenant traffic in a silo way, in a secure way, let's say, and to have separated traffic between the different tenants.
Yeah, I guess a different way of describing that is we're not necessarily thinking about wanting VPNs, but we're certainly wanting strict isolation between the underlay that the DPU is connected to and the overlay that's provided to the pods on the host.
Correct.
I guess, is there any concerns around that from any of the vendors in terms of limitations, or, is there anything along those lines that we should be worried about to accomplish that isolation?
Sorry, I missed the question. Can you repeat that question?
I was just wondering, was there any limitations or anything that would prevent us from being able to do that isolation or separation on the DPUs in terms of concerns around, I don't know, resources or anything along those lines? I'm just kind of opening the can of worms to see does anything come out.
Sorry, I had to kind of off from the few minutes ago, but for the network isolation, yeah, I agree. We need to support overlay like a VXLAN to provide network isolation. So that's one thing. And also we need to think about control plane isolation. What privilege we give to the host. So if it is accelerator model, then the host can probably have a privilege to control the DPU. But if it is like a tenant operator isolation model, then control plane also needs to be isolated from the host.
I mean, the control plane, as I see it, could be run in the IPU directly in the Linux subsystem of the IPU.
Right, I agree. And the point is the control plane can run on the IPU, but if it is accelerator model, then I think it's okay for the host side to be able to access to the control plane on IPU, because if there is no isolation of the tenant and the operator, if it is entire compute, including the DPUs owned by the user, then what they matter is just the accelerating and offloading, and then it can be controlled from the host. But if it is more like a tenant operator model, and the tenant doesn't own the DPU, and then control plane running on the IPU needs to be only accessible from the operator, at least for the control plane for the infrastructure controlled. I think the tenant can still control for the NIC level because NIC is already given to the tenant. But for the things like overlay setup or underlay networking setup through the IPU or DPU, that control plane should be only accessible from the tenant and not operator side.
Yeah, I don't see any harm to that, but we should make sure that we have proper separation. And I'm not sure if we can achieve that, but yeah, I don't see any harm.
Okay.
Want to continue? Yeah. Go ahead.
Yeah, so it sounds like from a high level viewpoint anyways, we have general consensus about the slow path in the DPU and the fact that, state will have to be reflected across that in the accelerated data plane. It sounds like we have relative agreement that in the case where we have isolated clusters for the tenant and the infrastructure, then we're going to have to separate the infrastructure networking from the tenant networking. And is that I think that's a fair summary of what we just discussed. So I'm going to move on to the next slide, which is a bit of a change of topic somewhat, unless somebody has a final note to add on this. Okay, so one thing we tried to look at was how would VF provisioning look like from the host's point of view if we had an isolated tenant cluster and an isolated infrastructure cluster. And so we tried to kind of draw out relatively, I guess, we had our nodes, our host servers, we have our DPUs on each node. We have Kubelet, obviously, for the tenant side running on the host servers, and Kubelet for the infrastructure, for the DPUs connected to the infrastructure control plane. And so one of the things that we tried to think about was potentially what we needed on the host server side to be able to request a VF from the infrastructure side. And we kind of came up with this concept of an XPU, I'm calling it a host controller, which is essentially just a daemon set that runs on each of the tenant nodes. And we would also have an equivalent daemon set called the XPU controller running on each of the DPU. I'm going to call them nodes now for the sake of simplicity. And really, the roles of this host controller and DPU controller would be essentially to reflect things like CRDs and resources across the two clusters. But before I dive into too much detail around, the specific roles of them, let's talk at a higher level about the infrastructure cluster and this very important component here called the operator. So the operator is kind of a key piece of what we see as the component that's tying the two clusters together. So, his role is really to deploy each of the XPU agent daemon sets on the DPU nodes. He might create, read, update, delete OPI CRDs in both Kube API servers. He will monitor Kubernetes resources in the tenant cluster. Potentially, he's translating incoming resources into OPI CRDs. We'll talk about this in a bit more detail in a moment. And he's also syncing back, CRDs that are updated from the tenant side, from the infrastructure side back to the tenant cluster. And then these XPU agents in the DPUs are also monitoring the incoming CRDs, translating those CRDs into real OPI API calls. And obviously they have some permissions to, CRUD OPI CRDs. On the host side, what we thought we would have in terms of, agents, I guess, or things working for the from the DPU, management point of view, I guess. We would have this host agent daemon set, which we saw on the previous diagram. He would also be able to create, update, delete OPI CRDs. He will also process certain requests, incoming requests from the device plugin or the CLI that will be running on the host side. The device plugin is another daemon set, unfortunately. This is a very standard Kubernetes thing that would provision and advertise all the VFs and sub functions to Kubernetes. It also interacts with the XPU host agent to invoke the creation of the OPI NetDev CRDs when pod allocation happens. And then the CNI, we've all heard of the CNIs, but it's at a very simplistic, its most simple operation, it would be to configure the interfaces with allocated IP addresses from the infrastructure and moving them from the host network namespace to the pod network namespace. Sorry. So if we go back to this diagram here for a moment and we think about, what happens when a kubelet tries to create a pod on the host side. So when the kubelet decides that it's going to create the pod on the host side, it would talk to the device plugin, because that's the thing that tells it what resources are available on the host side in terms of VFs and SFs. And it'll say, I want to allocate VF X for this pod. So the role of the device plugin at this point would be essentially to create something like an OPI CRD and send that OPI CRD to the Cube API server. The Cube API, sorry, apologies. It might be easier if we actually look through a sequence diagram, just so people are following what I say in a bit more detail.
Can I ask a quick question on the?
Sure.
So the previous picture, right, are we assuming that there is one cluster of host side kubelets, I guess, are the nodes, and then another cluster of nodes on the DPUs? I presume each, I mean, is it a strict boundary, or there could be a mix and match, right? I'm assuming there are different services that different clusters can offer, and there could be intermixing, right? I can very easily see two hosts plus, one DPU, forming something together, but because they're working on some specific function, right? I see a strict separation here. Are you implying anything, or it's just to explain and make it easy to discuss?
I'm not sure I understood the question fully, to be honest.
So, okay, so I'll repeat, right? So we connected the purples on the top and then the pinks at the bottom, using again funny terms for that, right? Is there any reason why it is strictly like that? I can imagine 2-3 clusters with different mix and match. It's just that, once all the bottom layers come up, Kubernetes is operating on top of these networking layers, right? When it is operating, it's a distributed system. You could be forming clusters of anything with anything else, right?
I guess you could. Like, the view we have is right now, this is the tenant cluster up here. So I just draw this line to separate it or to show it clearly. And below this line is an infrastructure cluster. And the role of the infrastructure cluster is to service the networking or to offload the tenant networking into the DPUs. Does that make sense?
Yeah, no, it makes sense. Maybe the question is that we're just talking one use case only, right? You're not saying this is a general case, right? In general, they may be a little more complicated, and you may have a mix and match scenarios happen. This cannot be the only way.
Yeah, I suggest let's label it. Yes, this is the first use case, and if there are any use, we are not precluding anything like that here. So let's let's try to deep dive.
To say it slightly differently, I guess this is the simplest infra tenant split 2-cluster scenario, but there's definitely scenarios where there's overlap and where you might have tenant workloads running on DPUs and vice versa. So yeah, there's definitely more complex scenarios.
Yep. Let's continue to the flow diagram.
Sorry, just one question. Imagine there was one node in that picture which did not have a DPU. How many clusters would it be a part of? 1 or 2?
So like a heterogeneous host here is what you're saying, like this.
Yeah, there was one without a DPU.
Yeah, so this is an interesting one. We can definitely talk about it in theory, because that's something that we've only discussed in theory between myself, Billy, and Donald as well. And so, like, ideally, we would want it to be part of the tenant cluster here. Like, this isn't just an isolated set of, I don't know, 10 servers. They're actually part of a bigger cluster set of different host servers and so on and so forth. And potentially, like, one thing that we were talking about, and this is just in theory, and obviously looking to the group for feedback and input, and would love to hear what other people like to think around some of this stuff. The idea of potentially, extending Kubernetes for the CNI to allow for delegate type CNIs, so that, you know, in the scenario here, the right CNI gets invoked to do the right networking for this host server versus, you know, here, what's actually happening is the infrastructure, the networking is offloaded to the DPU. Does that make sense, Venkat? Does that answer your question?
Thanks.
It's a good point, and I'm glad that you brought it up, because we need to put some effort into actually drawing the diagram that Mariam started sketching up there, which shows the heterogeneous tenant cluster. And it also, we've had a long discussion amongst the Mariam, Billy and myself around what this XPU Pink controller actually represents. And it obviously overlaps some with the functionality of the CNI's infra daemon set. And so some of that functionality would need to be deployed on a host that does not have a DPU. And that's where I guess we need to drill into the detail of that and try and come back with a diagram that shows how that might be modeled.
All right, let's move on.
Okay. Things might become easier with diagrams, or not, maybe more complicated. So this is just from a deployment point of view. I guess if we had the separate clusters, I just assumed that you know, the user would deploy the operator on the infra side. This operator would start a data syncer that would monitor the tenant resources. He'd also deploy this XPU controller, which is essentially the interface, let's say, to the OPI API. So this guy is going to be monitoring and watching for Kubernetes resources, either through CRDs or whatever, that are being reflected back from the tenant side, and making real OPI API calls, okay? And then on the tenant side, again, you know, you need an agent running on each node. So the role of this agent is also similarly to watch OPI CRDs. He's creating this gRPC server, which comes into play in the next steps when we look at pod creation and pod deletion. Essentially, I guess they're the main parts of the host agent, kind of syncing requests and monitoring requests, resources. On the tenant node as well, we have this device plugin, and as I mentioned, his role is to discover all of these VFs or subfunctions and basically register with the kubelet himself, so that he gets invoked every time a pod gets created. And he also sends the kubelet the device list of the VFs or DSFs. So then on the next stage, you know, if we look at what happens when we create a pod, and like, forgive me, this is probably like an oversimplified view, but I tried to keep it relatively simple and just focused on the host side. You know, very, very interested to draw out this part that goes to the right of the OPI API as well. But we haven't really gotten that far with it, really. So when a user creates pod, the kubelet decides which VF it's going to actually allocate. And it says to the device plugin, allocate this VF for this pod. And essentially what the device plugin is going to do here is it's going to interact with the gRPC server on the host agent. And what this will do is it'll indicate to the host controller that you need to create a NetDev CRD. This will be a new OPI CRD. This CRD will get pushed from the host controller all the way to the Kube API server for the tenant. Now, we know that this is already being monitored by the operator. So as soon as this update happens, a notify signal goes out to the operator to tell it that there's a new NetDev CRD available, basically. So the operator will pull down that CRD, and it has to push it to the local Cube API server at the moment. Now, like we can discuss different models around this, but let's just follow through with the sequence diagram for now, and maybe we can optimize it later. So the operator pushes the CRD to the Cube API server on the infrastructure side, who will notify the controller running on the node that there's a NetDev CRD available for it to process. So this is where it pulls it down, and it actually starts, generating the OPI API calls to, I'm saying create the NetDev, but obviously, I mean, these are physical resources. So it'll just set up the NetDev potentially. And we'll also ask the OPI API for the IP address for that NetDev. This is kind of important because I'd like to keep the CNI on the host side as simple as possible, not even doing IPAM, so that decision is driven from the infrastructure side, or at least the IP allocation piece decision is driven from the infrastructure side. So the NetDev CRD gets updated with the IP address. It pushes it back to the Cube API server on the infra side, which then gets synced to the operator, and from the operator gets pushed back to the tenant. On the tenant side, the host controller pulls down the updated NetDev CRD, and essentially it says to the device plugin that we're all good to go. Returns success, and he returns success to the kubelet, saying, yep, my VF is ready for the pod now. Kubelet goes ahead and starts creating the pod somewhere around this point. So the next thing that's going to happen here is that the CNI is going to get invoked, so that this VF now gets moved from the host network namespace to the pod namespace and gets its IP address set up. So a command add function call goes out to the CNI. The CNI is actually going to request the IP address from the XPU host agent, because that arrived down with the NetDev CRD that came all the way back from the infra side. So it just retrieves that IP address and sends it to the CNI, and then the CNI does the IP address allocation, movement of the NetDev from the host network namespace to the pod namespace, and it returns success. And voila, we have our pod up and running, and it has a VF that's provisioned from the DPU. And now the pod can start, and it can run off and start processing its application. Are people with me so far? Have I gone too far?
Toshi?
Yes, I think at the high level, this aligns pretty well with what I proposed before. So I think this is a really good starting point. Of course, in the detail, we may need to discuss, but I like the way you isolated tenant and operators. And I think this aligns pretty well with what I was thinking about.
Great. I mean, we were really trying to keep the host CNI as simple as possible,
Right, that's what I also tried in my proposal. So, and it also basically allows the direct attach of the VNIC to the pod. So that's also good. And yeah, I like the way you approached.
Okay, cool. That's interesting. And I appreciate the feedback.
And
because,
Miriam,
like,
will you be able to share the slides? I want to consult our Kubernetes expert.
Yeah, no problem. I'll be able to share the slides, and all of the sequence diagrams will be available in a Git repo publicly through links anyways, as I work them and rework them, so it's no problem.
Sorry, if you look at my original proposal and the sequence diagram, it's very high level, but it actually looks exactly like what you described.
Okay.
One question, this CRD that you mentioned here, is that unique per XPU or is it a common kind? If it's
Sorry,
common,
which field?
the CRD that's
This NetDev CRD.
yes. So
This
is
will
that
be
per XPU?
so it'll be created per VF request on the host side.
Okay.
So this will represent the host saying, I want a VF for my pod.
I guess it's an alternative to using annotations on the pod spec.
What was the original question though?
No, but is the CRD unique? I mean, the way I've seen CRD used is it's a resource kind. So this makes it look like, so if I have 10 DPUs, each of them with 10 VFs, do I have 100 CRDs? Is that how I interpret this? Or
You'd have a NetDev CRD per pod. So yes, if you've got 10 VFs, you've got 10 CRDs instances. Yes.
okay. Yeah,
Is
this
that a
a-
concern or?
oh, this is new to me. I didn't think people would create a CRD per instance. I thought the CRD was usually done for one kind of resource for the entire cluster. That's the way I've seen it done. This is new. That's hence my question.
I guess maybe the other way to phrase your question is that, how do you know which host to create a VF on without knowing where the pod is getting scheduled and all that? So is that handled in the sequence?
So you will have a lot of information. So it's interesting. I think it should be information contained within the CRD itself for the NetDev. So I mean, it's very rough. I don't want to share it so far because it's not ready for public consumption. But I think as part of that NetDev is that it should tell you like things like the serial number, like it should identify the VF uniquely using something that we discussed this in the group as well, like the serial number, the PF ID, and the VF ID, just to uniquely identify the VF on the host side, which I presume is something that is potentially reflected accurately on the DPU side. I would look for guidance from you guys, at least.
Uniquely across the cluster, right?
Yes.
Mm.
And then the other thing that, I mean, it's very easy to retrieve host information from here to put it into a NetDev CRD and say, this is the host I'm on. You're potentially using labels or actual fields in the CRD to say, this is the host that I want to service. And then, I guess the agents here, it's up to them to understand that there is somewhere a relative mapping between host and the DPU. So it would recognize that this is my host and I need to create a VF. Does that kind of address what you're talking about, Vipin, or is that what you were thinking about?
Yeah, I'm okay with specifying the PF details so that host can create a specific thing. I guess my question was, how does a person who's creating a CRD know exactly that this is the host on which I have to create the CRD? Or are you suggesting that we are going to create like a whole bunch of VFs
okay, I see what you say.
Various nodes?
So,
yeah.
So this CRD is not created by a person. This CRD is actually created by the host agent, and it gets enough information to create that CRD from the device plugin running on the node itself. So this is all, these are privileged daemon sets, that are capable of retrieving enough information to reflect.
Got it.
Yeah.
Okay, that makes sense. Thanks.
Yeah, just
regarding
to-
the mapping, sorry, Bill. Regarding
you-
the mapping, I understand that we had already the conversation and the issue was raised. The mapping between the virtual and physical function that DPU knows versus the PCI Express BDF allocation that happens on the host. So
Yeah.
So I'm not. This is still, I think, an open question. I'm not sure we have currently identified a clear way how to do the mapping between the BDF on the host and physical virtual functions on the DPUs.
Yeah, no, I think it's really important. It's an important one, and I totally understand the issue of enumeration being different because of the different OSs essentially running on what looks like different nodes. But it's a really important one, you know, because even from the tenant node point of view, when we can't track VFs using just like an IF index. And I guess PCI addresses can change if you hot plug stuff, but IF index is not unique across namespaces. And so having something that is truly unique to identify the VF and to map that between the host domain and the DPU domain is really super important. Sorry, Billy, you were going to say something.
I was just going to ask Boris if that was being tracked here in the API group, or did that come up in the lifecycle management group when you said that's already been discussed and we haven't got an answer yet?
Yeah, we discussed it at several forums. I don't remember which specifically.
Okay,
We can either keep the discussion here or move it there. I don't really mind as long as we solve it. So
yeah, I think the point though is we assume that gets solved. I mean, it's going to have to get solved, so we will leverage whatever is used there.
yeah, I understand.
Yeah, and I guess the only other thing that we haven't really seen before was this concept of the device plugins. You know, but I think it's kind of a really interesting one because it gives us a hook point at pod creation time, you know, naturally through the existing Cube APIs, you know, so I think it's kind of just an interesting one. Do we want to go through pod deletion? Do we have time? No, we don't. It's already time.
We're at the top of the hour. Yeah.
Yeah.
So yeah, first of all, thank you. I think this was very educational. If you can share the slides again, we can all try to offline think about that. The recording, obviously I'll post it. Miriam, if you can share the slides, I can also post it on GitHub as well. All the diagrams and everything will be shared, as Miriam said. So if people feel this is kind of good topic, maybe next week we can do 2 of those discussions again. Maybe we can sacrifice lifecycle time slot again. It's up to you. So comment in Slack and see you next week.
Thank you.
Thanks, everyone.